I'm Ronald Sampson, Vice Chairman Technical of the 15th Electronic Insulation Conference. It gives me great pleasure to introduce one of the prize-winning papers of the 1981 conference. The paper was presented by Richard V. Edwin, Senior Project Manager for PCK Technology Division of Cole Morgan Corporation, and is entitled Past, Present, and Future of Printed Circuit Board Technology.
Today, printed wiring is used everywhere. It is the main building block of any electronic system. As far as we can see, its popularity is expected to continue growing for at least the next 5 years. Printed wiring constituted over 2.5% of the cost of all electronic equipment in the U.S. in 1979, and it's expected to grow by 1984 to more than 3.5% of the total value of U.S. electronic shipments. This situation is reflected in the size of the U.S. market for printed wiring boards, which in 1980 was estimated to be in excess of $2.5 billion. It is forecasted by Gnostic Concepts that it will double by 1984 and be over $5 billion. A chart showing this forecast growth for electronics, integrated circuits, and printed wiring is shown in this first slide. And a forecast of the market board by type is shown in the next slide. In addition to this table, shows the ratio of high-density printed wiring to total printed wiring and the projected growth of printed wiring as a percentage of total electronics. U.S. printed wiring shipments in 1981, by most projections, were expected to increase about 7.5% in dollar value and little or none in board volume. The increase for 1982 is forecast at 16% over 1981 board value. In spite of flat overall sales in 1981, an increase of 30% in multilayer shipment value is expected. Just over 50% of multilayers are the 4-layer type, while those with more than 9 layers represent less than 10% of the market. A few denser and more complex boards are manufactured, but these are not typical. Epoxy fiberglass is the predominant laminate, accounting for about 80% of total area shipped. Composites are holding steady at 14%, and paper-based laminates are declining, holding only 4% of total area. Thin foil, high performance, and additive laminates account for the remaining sales, which are less than 2%. One of the reasons for such extensive use of printed wiring boards, which makes them the most universal interconnection method. One of the reasons is the exponential growth of component terminals to be interconnected. According to Gnostic Concepts, in 1970, a total of 37 billion terminals had to be interconnected. In 1978, we crossed the 100 billion mark, and in 5 years from that time, or by 1983, we will double this number again. The lion's portion, over 90% of these, will be integrated circuit terminals. That precipitous growth is certainly caused by the rapid introduction of LSI and microprocessors, each requiring more and more terminals per package. And again, 90% of all component terminations are made on printed circuit boards, guaranteeing their growth, but also placing strain on this technology. A very important factor in favor of printed wiring boards is that they are extremely well suited for present assembly and testing methods. An entire fast-growing automatic insertion and automatic testing industry is based on the form factors of printed wiring boards, making them an efficient element of their electronic equipment manufacture. But the main underlying cause of printed wiring growth is the extremely fast proliferation of electronic applications in all aspects of life, at home, at work, and in the car in between. This is the result of great advances made in IC device technology and will be accelerating with the introduction of VLSIs, VLSIs, and microcomputers. Every new or unsuspected use of ICs or LSIs requires a printed wiring board to mount them on. In the past year, or the past decade, we've learned a great deal about how to make better printed wiring boards and how to improve their manufacture. The list of technical advances in this field during the past 10 years is very long, but in the rush to manufacture higher quantities of boards and to make them work better, we've missed an interesting fact. Most of the important innovations which have provided quantum advancement or which have opened conceptually new departures in electronic packaging fields were all made before 1970. Multilayers, additive processes, wire wrap, multi-wire, computer-aided design, hybrid circuits, flex rigid systems were all developed in the 1960s. Only their increased utilization came about in the 70s. Technical innovations of the 70s, while important, have not materially changed printed wiring boards' physical or cost structure. As a result, I think that we're now entering a turbulent period in electronic packaging where new demands on interconnection capabilities will challenge these established ways. A variety of forces are causing this upheaval. Some of these are, number one, that interconnection costs have not followed the IC device cost decline. Today, a computer on a chip costs less than many of the surrounding components and devices. Therefore, the competitive edge today is shifting toward the ways the design engineer is coping with system interconnection problems. There is a strong trend toward increased usage of the faster operating types of IC devices, emitter-coupled logic and others. It is inefficient to lose their advantages due to propagation delays in the wiring. Therefore, to fit the device capabilities, the interconnections serving them should have specific configurations, making it possible to locate all the devices within a very limited area. Further integration of functions is also limited by considerations of the economical size of units removable for field maintainability, changes, or for repair. While the DIP PC board combination is still efficient for discrete components and for most of the present IC devices, the VLSI packages having 40 and up to 150 leads cannot be efficiently packaged in a familiar DIP configuration with 2 rows of leads spaced on 100 mil centers. This situation has resulted in considerable activity aiming to change the shape of packages for complex chips. There is a new breed of device packages coming into the market. They're called QIPs or tabs and predominantly CCCs or chip carriers. Chip carriers are square and have terminal spacings on 40 or 50 mil centers. They reduce space requirements, reduce lead length, and they're pre-testable and pluggable. That is, they possess a number of desirable features and they are proliferating rapidly. Of course, this reduced component package area cannot be fully utilized unless increased connectability and improved heat extraction is provided by the next level of interconnection. Any increase in leads per package calls for increased interconnections between them, as shown in this next table. Connective capacity in this table is the maximum amount of wiring channels which can be placed in 1 inch. For example, on a 50 mil grid, 20 conductors will fit in 1 inch. If there are obstacles, such as plated through holes, then the connective capacity is reduced considerably in actual designs. Providing 3 or even more conductors per channel in dense printed circuit boards requires extremely narrow conductors and spaces. This requirement escalates the difficulty of maintaining the continuity of traces and in preventing shorts between them. This ability to economically provide this contrast between conducting and insulated areas of a circuit is the main condition for successful adaptation of any interconnection method in future designs. Now that we have established a general picture of present and future market situations, we will attempt to find indicators which may bear on the future developments of printed wiring and overall interconnection technology. First of all, the printed wiring board technology as presently practiced will continue to be used in the future, albeit with some refinements and improvements. Certainly it will not disappear. While printed wiring board growth rate may not be as spectacular as before now, since their manufacture is becoming a mature technology, there will still be a reasonably large market for printed circuits in the coming decade, as I have shown in the previous charts and tables. The subject of further discussion here will be the leading edge of interconnection technology, which will be applied to new, challenging designs, and which, if successful, will have a much faster rate of growth than the more established technologies. The advances made in condensation of more functions on a single IC chip results in drastic decreases in the size of electronic equipment. Therefore, the cost multipliers which had to be paid for hardware, connectors, cables, cabinets, are also being drastically reduced. As seen in this next table, the cost of interconnections rises almost exponentially with the distance from the chip. Present designs that can thus eliminate all these expensive interconnections and suck them into the printed wiring board, resulting in a proliferation of what is called single-board electronics. A great deal of activity is emerging in the U.S. to customize the LSI devices and to replace more interconnections from boards onto silicon. As clearly indicated here in the chart, the major incentive for all this activity is to cut the costs of interconnections. Personal or consumer circuit boards, those characterized as having 1 to 10 ICs per system, are generally small, 1 or 2-sided, mass-produced boards, and they are usually not repaired. The boards for system applications, by contrast, are typically large and quite complex and must be repaired and maintained in the field. The increased conductor density demands here not only stem from LSI device interconnection demands, but also by the need to accommodate additional connections for onboard diagnostics and through absorption of interconnections which were previously external to the board and which now have become an integral part of the single board electronics. Unfortunately, dense and large systems boards cannot easily be repaired, and they are costly to exchange in the field or to store in depots. With the present exchangeable boards approach, it's estimated that major electronics firms have about 5% of their total assets tied up in repair depots and replacement pipelines. The new field exchangeable unit must be the device itself to reduce the economic burden of equipment maintenance. The problem of heat management of the electronic systems is becoming progressively worse as more and more functions are crowded on the chip. Many VLSI packages containing very complex circuits are generating up to 3 watts of heat. To explore their packaging potential fully, it's desirable to mount the packages close together on the substrates, which in many cases may reach 2 or 3 watts per square inch. The dissipative capacity of presently used printed wiring substrates is woefully inadequate in comparison with ceramic or metal. The thermal resistance of epoxy boards is about 50 degrees centigrade per watt, or double the resistance of ceramics. To bypass this problem, large heat sinking structures are being added to VLSI packages. These take away valuable space, increase board-to-board distances, and reduce the overall component density of the system. In the same way, forced air cooling requires additional room and expense, also reducing packaging efficiency of the overall electronic system. With air cooling, noise levels can become distracting, and the amount of cooling for newer systems may require moving air at supersonic velocities. For these reasons, considerable efforts are being made to use the interconnection substrates as heat conductors, since convection cooling methods are approaching their useful limits. The operating speed of all electronic equipment, complex or simple, is constantly rising, not only because it's needed, but because it's increasingly available. The use of an especially fast IC family, emitter-coupled logic, is gradually increasing, although they only represent now about 10% of current IC use. However, with MOS and other IC types being continually redesigned by reduced geometries, they are permitting ever faster rise times, and packages are being miniaturized. Designers do not like to dilute these built-in advantages by wide fan-outs and long interconnection paths. As a consequence, the physical packaging becomes an important part of device and system operation. I've covered some of the more important needs of current system packaging. Interconnection methods are strongly dependent on the shapes of the device packages they have to assemble. In the past few years, a concentrated effort has been going on to resolve the question of how to emerge from a very complex chip and how to connect this multifunctional chip to the world. As a result, a variety of IC package forms and formats have been developed to resolve the mounting input-output problems of these new VLSI chips, which may have up to 200 terminals. Some chip connection methods are relatively old, such as the suddenly popular IBM flip chip method, where chips with solder bumps are attached face down onto ceramic substrates. Others are relatively new, such as tape automated bonding, or TAB, where chips are secured on frames made in film strips, and then tested, cut out, and secured onto ceramic or printed wiring interconnecting substrates. A third method, rapidly gaining popularity, is the ceramic chip carrier, or CCC, as I described earlier. Since VLSI chips require from 40 to about 200 I/O points, the use of customary dip technology for packaging of these circuits would have resulted in excessive board area and conductor lengths for fan-outs. In contrast with dips, use of the new chip carrier format reduces the area of the VLSI package by a factor of 2 to 5, and it reduces weight by a factor of 7 to 10, with a corresponding reduction in lead length and ultimately in cost. Some firms have announced plastic types of chip carriers, or PLCCs, and Signetics has revived the small outline or mini dip package for many analog circuits. All this activity indicates a rather rapid acceptance of small, compact packages with terminals spaced at intervals less than 100 mils to save area, weight, and cost of IC packaging and to improve electrical characteristics. The next table indicates a view of some forecasters about the rate of proliferation of these packages throughout the world market. From this table, it is clear that dips will not be extinct at all, and actually their use will be greater than in 1980, when approximately 6 billion dips were assembled into equipment. On the other hand, it indicates that there will be, by the end of the decade, a sizable need to interconnect somewhere upward of 10 billion devices packaged with these new configurations. The matter of terminal spacing on the new packages has not yet been settled. The original design of chip carriers was with terminals spaced on 50 mil centers around the entire periphery. This is the JEDEC standard for chip carriers to be interconnected by circuit boards. Now there's a second approved family of chip carriers with terminal spacing on 40 mil centers, mainly for ceramic substrates. As the demand for more I/Os grows, even the present chip carriers become too large with 200 or more terminals. For these cases, a new standard is being readied for chip carriers with terminals spaced on 20 and 25 mil centers. Tab lead separation is usually 20 mils, but there are some newer variations and new versions with 10 mil spacing between leads, and these are already close to the flip chip separation, which is 8 to 10 mil centers. It's obvious from these developments and directions that in order to accommodate the most stringent termination system, the new interconnection methods for the 80s must have a capability to handle 10 mil terminal spacings. Already today, one of the obstacles in the use of chip carriers is the absence of a clear-cut and elegant way to mount them on a suitable interconnecting substrate. The thermal mismatch between the ceramic carrier and the plastic of the circuit board prevents their direct mounting onto conventional printed wiring. This next table indicates the thermal coefficient of expansion of various materials. As we can see here, the mismatch between a 1-inch chip carrier and the circuit board at 100 degrees C temperature excursion will result in movement exceeding 1 mil, causing stresses on solder joints strong enough to break them. The sockets with compliant leads used presently to alleviate this problem add an additional level of interconnection and cost. Besides, most users want to have direct chip carrier attachment to the substrate to achieve easier attachment, lower profile, and better heat dissipation. Presently, this is achieved on ceramic substrates, but this is also not an ultimate solution since there is a severe size limitation and there are electrical restraints of ceramic substrates. Surface mounting and attachment of components is a very logical development, and it receives wide attention. The absence of component leads provides a number of benefits such as simplification of shipping and handling, speeding up of assembly, simplifying soldering, and eliminating the need for component holes in interconnecting substrates. The absence of component leads may have a profound effect on the connective capacity of interconnecting substrates and could considerably change the methods and structures used for device interconnections in the future. The next table illustrates the effect of removal of the component holes from their surrounding pads and substrates, and their surrounding pads from substrates, and replacing them with vias which do not take up any more area than the conductor itself. This table indicates that under these conditions, the desired conductor density can be provided with easily manufacturable conductor widths and spacings, or that a doubling of density can be achieved while still using the same conductor widths and spacings as would have been required to pass through the tight areas between the pads. There is also a strong movement, especially in Japan, to use discrete components in surface attachable chip form. These provide all the above listed benefits, and they make it possible to construct entire systems solely using surface attachment. Earlier I showed a table showing the impact of terminal condensation on wiring density, or on connectivity, which is expressed in the total length of conductors per square inch. For the sake of variety, I'd like to show the same same facts in a different format in this next table. This table indicates that the interconnection of dips requires 40 inches per square inch of wiring. That is 40 inches of wiring per square inch of circuit board. This can be accommodated today by 2- and 4-layer boards. When using chip carriers with 50 mil spacing, the needed wiring capacity grows to 160 inches per square inch. Complex multi-layers and present multi-wire can only accommodate up to about 120 inches per square inch of wiring. For connectivity demands beyond that, new methods must be developed. Consider also the tab connectivity demands rising way above 200 inches per square inch, with terminals on 20 mil centers. What will be the connectivity demands for the future VLSI packages having terminals on 10 mil centers? Considering all the trends that I've listed and the demands of systems and device packaging, we can ascertain some of the directions of future developments. Under additive techniques, I also include both fully additive and semi-additive and ultra-thin foil processes. Semi-additive processing is essentially identical to standard plated through hole board manufacture, with the exceptions that no solder plating is required, and only 1/10 of a mil of electrolysely deposited copper has to be etched from the background, thus permitting easy manufacture of high-density circuits with thin conductors. The thin conductors made semi-additively also have the advantage of nearly rectangular cross-sections and minimal deviation from the artwork or design conductor widths, properties which are important in controlled impedance and microwave circuitry. Semi-additive processing is also uniquely applicable to producing circuitry on the many new thermoplastic substrates which will be introduced in the 1980s. The greatest potential for manufacture of boards with increased density of conductors is provided by the fully additive processes, where the entire conductor thickness is deposited chemically from an electroless copper bath. The advantage of electroless plating in high-density applications is that the conductor fidelity is dependent only on the resist resolution limits. There are no deposit variations caused by field distribution or pattern density, which are typical of electroplating processes. An additional benefit of electroless metal deposition is the ability to provide extremely uniform layers of copper in the barrel of the plated hole. In recent papers, IBM has demonstrated that adequate and uniform CC4 electroless copper plating in multilayer boards can be achieved with hole depth to diameter aspect ratios of 11:1, as well as 4 mil line widths, and that these have been achieved in production quantities. A serious obstacle for the further increase of connection density is the familiar plated through hole and the pad around it. The pad size restricts the number of wireways which may be placed between holes. Because of density constraints caused by close lead spacing and component holes, there is a growing tendency toward designing components for surface attachment instead of using leads or pins. In these cases, the plated through hole diameters can be reduced considerably since they are used only as vias between interconnection levels. The combination of surface attachment of components and the use of sequential deposition of conductive and dielectric layers are opening new avenues for developing interconnection structures. Using these techniques, multi-layer structures can be achieved without holes, or two-sided board equivalents can be made on the single side of a substrate. The fastest growth rate from all types of printed wiring boards is for multi-layers, and especially for four-layer multi-layers. The fast growth of four-layer multis is explained by their ability to provide microstrip transmission line configurations in high-speed applications, and the ability to provide at reasonable cost more room for logic interconnections on the two external surfaces by embedding the ground and power planes within the laminate. As system complexity increases, however, and the available area remains limited, the connections provided on a four-layer board become inadequate, calling for the use of complex boards having 6, 10, or more layers. In order to connect chip carriers reliably, substrates will have to be much more dimensionally stable than is presently possible with polymeric-based laminates, and will have to be made of materials which match the thermal coefficient of expansion of ceramics. These substrates must also serve as efficient heat conductors to liquid chilling systems, and must be able to accept surface-mountable components solely or in combination with leaded components. All of these attributes can be met only with metal core substrates. Since surface attachment alleviates the need for through holes, metal substrates could become extremely cost-effective for chip carrier applications. It's too early to say whether polymeric or porcelain versions will gain predominance, but the electrical flexibility, manufacturability, and cost considerations give an edge to the plastic types, or the polymeric types. Other interconnection techniques which do not employ graphic means of pattern formation are becoming increasingly popular. Such techniques as stitch welding, stitch wire, solder wrap, and multi-wire have been popularized in the past few years. These use insulated wire to provide logic interconnections on the circuit board, having only power and ground distribution made by graphic means. A brief description of the multi-wire system will provide you with an understanding of what discrete wiring systems have to offer. This process is an automated interconnection system in which 6 mil or smaller polyimide insulated magnet wire is laid down on an adhesive-coated substrate with etched power and ground planes. Component insertion holes and wire terminations are formed by drilling through the wire and the board and electrolessly plating the hole walls. The unlimited crossovers permitted by the use of insulated wire allows placing a very dense matrix of interconnection on each wiring surface, equivalent to 3 or 4 multi-layer logic layers for each wiring level. It also simplifies greatly the design of such boards, permitting the use of computers to reduce time and cost of tooling and to totally eliminate costly artwork. In the multi-wire system, therefore, an increase in the conductor density requires only an arithmetic progression of cost, in contrast to prevalent graphic techniques which require geometric increases in the cost to accommodate higher levels of density. In addition, the uniform wire cross-sections, predetermined and level locations of wires above ground planes, provide a controlled impedance microstrip transmission line effect in multi-wire boards. Additional methods are also being developed to cope with the high-density packaging problems which I described earlier. In the LAMPAC approach, a thin two-sided flexible circuit of approximately 5 mils thickness is bonded to an epoxy-coated metal support. The key here is separation of the load-bearing structure, the coated metal, from the electrical interconnection function, the thin flex circuit. The thin circuit material permits efficient manufacture of small holes connecting traces on its two surfaces. The vias are small enough to be accommodated without interrupting channeling capacity, thus providing sufficient density to interconnect complex chip carriers. LAMPAC could be a very cost-efficient method for interconnecting chip carriers. The PHELPS technique provides an extremely dense 3 to 4 mil wide traces multi-layer conductor package in polyimide material by using the build-up post technique for layer-to-layer interconnection. Due to a complex manufacturing process, single source, and low volume production, however, it has limited application and it has not yet been proven to be cost effective. Microwire, a new method developed by PCK Technology, uses a combination of discrete wired dense interconnections on substrates which match the thermal expansion of ceramic chip carriers. Like Lampak, Pactel, and other high-density interconnection systems supported on metal planes, microwire achieves a thin circuit layer, not more than 15 mils thick, so that the characteristics of the metal support plane, thermal expansion and heat dissipation, are dominant. This is achieved by the use of high-density wiring using wire of 4 mil diameter or less with 10 mil diameter access vias, which are required only at component pad points, thus ensuring minimum interruption to track routing. Wiring densities of up to 160 inches per square inch are achievable using a 12.5 mil grid for conductor routing. Microwire, like its parent multiwire, also has the advantage of not using artwork for signal layers since the entire design and wiring process is computer generated and controlled. This makes engineering changes easy and shortens the increasingly important product development time. The availability of microwire offers a versatile large area interconnection system tailored to the needs of leadless chip carriers. It provides area and electrical characteristics like printed circuits, thick film multi-layer density, thermal match to ceramics, and rapid design or design modification turnaround. This presentation has attempted to focus your attention on new demands which are being placed on interconnecting substrates by rapid advances in VLSI technology and packaging approaches for such devices. These demands will be tough to meet by direct extension of presently used interconnection techniques. Realization of this has prompted us to make an intensive search for alternatives. The analysis of presently visible needs shows that some possible avenues of development to resolve these needs. The work is cut out for us to bring such methods to practical reality.